My name's Tyler Hudson. As you mentioned, I'm a materials research engineer at NASA Langley. And what I'm going to be talking to you about today is porosity detection during the composite cure cycle, as well as cure monitoring, all happening in either an oven or an autoclave. So a challenge, many of you, if you're on the manufacturing side of wind energy, know that wind turbine blades are made out of composite materials. You make them out of composites for their advantages in fracture toughness, fatigue strength, lighter weight. However, due to their large size and varying thickness, you can have under or over cure in certain areas of your wind turbine blades, as well as defects present inside the composite. And that's actually what the three images at the bottom are. So this would be a highly porous or a laminate that has a lot of voids marked to these dark areas. On the left-hand side, a laminate with moderate porosity, and then whatever one is shooting for, so a composite laminate with very low voids. Prior to the invention of the system that you heard about today, there was no direct measurement technique of porosity or other defects during the cure cycle. And the takeaway is current inspection processes for wind turbine blades do not occur until after cure. And if defects are present, expensive rework up to actually scrapping the part could happen. Just a brief history. I'm not going to go into a lot of detail other than to mention that there's two systems. The third system is the one you're going to hear about today. That's really focused on the aspect of being able to do defect detection, as well as high spatial resolution cure monitoring. But there was a system before this one that could do cure monitoring using embedded optical fibers. If you're interested in that technology, don't hesitate to reach out. But today's presentation is going to focus on this third system. And then the takeaway is the second system really could focus on like life cycle monitoring, so your sensors stay in the part after manufacture. The third system is really focused on being able to do that defect detection. So here's the objective of the system is to be able to detect, localize, and quantify defects such as porosity during the cure cycle. And this is hard primarily because of the harsh environment of cure. So this is kind of a PowerPoint drawing of what the system looks like. You have your composite part that you're making. You're inspecting it using an ultrasound transducer, and there are electronics inside this housing. And those electronics are the ones that would not operate at 350 Fahrenheit and up to 100 PSI. We cool those electronics using a liquid nitrogen cooling system. And it's a really elegant cooling design in the fact that most autoclaves are nitrogen environment, but this could work in autoclave or oven. And really the takeaway is the system is designed to operate within existing state-of-art cure processing equipment, such as autoclaves or ovens. And it's designed to be bolted onto your existing production technique. You're not going to have to go in and completely change the way that you're making your composites. This is just data to your production system. So here's a picture of what the system actually looks like. So this is this housing that has all of the electronics. That's what is cooled. Your ultrasound transducer is in this configuration is on the tool side. It can be on the part side as well, and it sends ultrasonic waves through the tool plate into the composite, measures that reflection, and then rasters left and right, and then in and out of the enclosure to give you an image of what the internal structure of your composite looks like. And then the key takeaway is that the existing prototype is already operational in a relevant production environment. NASA's TRL system is a TRL-6. Our autoclave testing, this kind of puts it all together in just a really simple slide. So we have process models that can predict porosity throughout the entire cure cycle. If you pull out a single point, so this is when in the B stage, when your resin is still liquid, we're doing inspections throughout the entire cure. If we pull out the particular scan, that's at the same time in cure. This is one surface of the composite. This is the other surface of the composite. And what you notice is this on this back surface of the composite, you have two areas of high porosity denoted here by a low amplitude, and in the center denoted by a low amplitude. And that corresponds exactly to where the porosity is predicted from the process model. This is a through thickness view. We also can get top views of your laminates. Again, the through thickness and the top view line up. We can compare this top view to existing commercial UT systems after cure. So this is what's primarily done on composite structures right now after cure. And then we also took the same laminate and cut it. Might have looked at the through thickness section, put it under a microscope, and showed those three areas. And you can see the high porosity corresponding to this area with the very low amplitude, the low porosity corresponding to high amplitude, and then the moderate porosity in the center, which is really what this shows is that we're able to detect even very low percentages of porosity using this system. And the takeaway is that we have a validated testing inspection method, and we validated it against process modeling simulations, state-of-art commercial ultrasound systems, as well as optical micrographs. So we're very confident in the results that we're getting. We also did oven testing, and primarily the reason I'm showing this slide is for two reasons. So one, this image here shows that clearly that you can also not only determine where a defect is at spatially, but also through the thickness. So this is one surface of the composite. This is the other surface of the composite. And then you can see these three defects at varying thickness. This is about 25% of the way through, right at the mid plane, and then 75% of the way through the thickness. And this is done on out of autoclave composites, and most wind turbine blades are out of autoclave processing techniques. So in summary, we developed a system that can perform defect detection, localization, and quantification during the cure cycle. And that's really the emphasis here. There are existing commercial systems that can do it after cure, but this really moves that inspection from the end of the cycle to when there's nothing you can do about it back into the during the cure. And so in addition to defect detection, it also features very high spatial resolution cure monitoring of resin state. So you can determine whether your resin is liquid, rubbery, or solid. You can pick up things like viscosity, degree of cure, glass transition temperature, all on a very, very small spatial resolution. So each pixel is like 1 millimeter by 1 millimeter in our setup, and you can do this over large areas of your structure. The system's already scalable from an R&D to existing production lines. We have it installed in production equipment at NASA Langley, and then this is a key feature, is that there's no change required to your current part design, and only minor changes to your processing equipment. So there might be some minor changes to the tooling, so the system can bolt on and inspect through the tool, but you're not changing how you're making your composites or the equipment that you're currently using to do that. It's really an add-on that can provide this capability. So what does this provide? It gives you a real-time knowledge throughout the cure. You can use that knowledge to either validate process models. Maybe you've got a process model of your system, or maybe a key feature. We've used it a lot internally to determine processing parameters during certification. So as you're developing what is the ideal way to make your wind turbine blade, you can use this data to feed back in and come up with that idealized or that optimized process quicker than you would in a trial and error based technique. In production, you could actually control your processing parameters based on that feedback, and we've done that on a few of our projects as well, using this ultrasound data to determine changes to your cure cycle. And all of this results in a more efficient process development, a shortened certification time, a reduction in off-spec parts, whether that's defects or over cure, reduced production costs, and increased production throughput. And that's really where it all matters. It comes down to how much it costs and how fast can you make it. So commercialization, naturally, this presentation is focused on wind turbine blades, but the system itself can be applied to aircraft, launch vehicles, satellite buses, automotive, really any structural composite. As with any invention, it's never one person. So I had people within NASA as well as interns helping me on developing this system. And here is my contact information. Feel free to talk to me during the meeting after the presentations are over, or reach out via email or phone. And with that, I'm going to stop talking and I'm going to hand this over to Dr. Chris Wohl to present on his technology.
Awesome. Thank you very much. So it's really great. I'm really happy to be talking with everybody this afternoon. Tyler just talked about some of the technologies that he and his team have developed to help with process monitoring to make sure that you'll be able to fabricate highly reliable wind turbine blades. And then right after that, you guys are going to hear from Grady, who's going to talk about ways to protect those blades from wind events so that you can keep those wind turbines operating efficiently. I'm going to talk to you about kind of right in between, and that's going to be technologies to help with contamination prevention. We want to keep those wind turbines operating at the highest efficiency possible, right? And so the things that can play a role in contaminating those surfaces are insects, ice, birds, dirt, and dust. And admittedly, this picture for dirt and dust is from Mars. I don't think there's going to be much Martian dirt floating around here on Earth, but we do have Earth dirt that we'll have to focus on. So I heard recently for orientation that they're talking about changing the orientation of wind turbines from spinning vertically to spinning horizontally as a way to help offset bird strikes and hitting honeybees and all. So there's potentially some good technology development activity there as well. But what I am going to be briefly going over today, and would be happy to address any follow-on questions anybody might have, is a series of technologies that myself, along with many others, as Tyler mentioned, none of us do this alone, really looking at different material systems with different focal points for contamination prevention. Some of these are ice, some are dust, some are insects, some cover several contaminants. And we'll just kind of briefly walk through a few of those. But I'd be happy to share this list later if anybody is interested. And of course, you can reach out to the technology transfer folks. They'd be happy to provide additional information. When we talk about contamination, though, it's really important that we understand the process itself. And I want to emphasize this is a dynamic process, right? So over on the far left here, what you guys can see is that if you are looking at, say, an insect hitting a surface or a water droplet or a dust particle, it's a dynamic event. And so if we can understand more about that process, what we can do is modify our surface, modify a coating, modify topography, something like that, to help address the adhesion promotion aspects of that at different stages of that impact event. The two primary ways that we've done that are by changing surface chemistry. And this is really important. I'll touch on this a little bit more. It modifies the surface chemical processes and not the bulk processes. This is an important thing, especially if you're concerned about how a coating might impact the environment, something that we've tried to keep in mind as we've developed a lot of these coatings for commercial aircraft operations. So being able to just tailor that modification to the surface is important. The other thing that you can do, the other easy wheel to turn, is surface topography. So you can do that in a controlled fashion, what I'm showing up here. Pattern topographical modification using a laser. We've also used other techniques. But then there's also ways that you can impart topography randomly by putting filler materials or other topographical modifying agents into your coating formulation. And so we've explored that as well. So now that we understand the process for contamination, we've developed approaches based on the physics of these impact events, how we can best mitigate adhesion. Now we need to come up with tests to evaluate that. And so we have the primary objective, right? We want to make sure that insects don't stick, ice doesn't stick, dirt particles don't stick. But then we also have secondary objectives, right? We want to make sure that the coatings that we're generating, these technologies that we're developing, are translatable from the laboratory environment to an operational environment. And that's where durability really plays a central role in a lot of these applications. But let's walk through some of those contaminants. The first I'll talk about is insect impacts. And you don't think about this, right? You have your car, insects hit the front, your gasket doesn't really change much, but it can have a dramatic influence on energy production. So all of that investment and all that potential value that you would get from your wind farm can be reduced by up to 55% just from the increase in drag from insect residues, right? And so I have a couple of videos to show you here. So the first will just be a regular uncoated aluminum surface. So you can see the insect comes in, all this area here, all this topography that's covered in those residues is now not only potentially contributing to drag, but also will be a great anchor for the next insect residues that could hit this surface. We'll move on here. This is a surface that has been modified using this technology here. So this is a hierarchical topographically modified epoxy surface, and you can see far less residue. We've changed that impact event, and as a result, the increase in drag is going to be reduced, and also the surface contamination, which could accelerate additional contamination, has been reduced. And so there's a really promising aspect of this for the longevity of that coating between cleanings as well. The next one is ice, and ice is a really big deal. It can do a lot of damage to the mechanisms of your wind turbine. It can damage the blades. It can cause full stop, right? So your energy production goes from whatever it was to zero because you had to turn your equipment off. It can also, if the large pieces of ice fall off of one blade, they can damage another. They could hurt somebody. They could damage surrounding infrastructure. So this is a really important aspect of keeping a wind turbine functional and as efficient as possible, so that the investment that you put into that can be as great as possible. So what we have here, we have developed an instrument that can do impact icing experiments. So here down at the bottom, you can see that there is a control sample that collects ice, and then our experimental sample that ice will come off of. And it is the detachment of this ice that we detect. Over here on the right, I've shown a couple of our durable epoxy coatings. This is a different technology. And there's very, very little ice that has accumulated on these surfaces. And the key thing with this is that if little ice can attach, but if little ice can accrete before it detaches from your surface, anything that falls off of it is going to have a much lower risk of damage. It's also going to, while it's attached, significantly reduce any kind of imbalance or disruption in aerodynamics that is experienced by that wind turbine. Finally, let's talk about dust, right? And so we know that dust can be very abrasive particles. These things can increase drag, and what that means for translation to energy production is that as the drag goes up, the energy production goes down for the same amount of wind energy available, right? So we have surfaces that have a lower propensity to retain dust particles as they're adhering to them, again, reducing the change in those aerodynamic properties. Ideally, it would reduce the increase in drag as a result of, say, experiencing a dust storm or something like that. And we've developed this experiment to evaluate these technologies so that we can say, yes, the topographies that we're generating that I'm showing here on the right-hand side for both the polymeric surface and the titanium surface will reduce the adhesive interaction of an incoming dust particle. And again, the idea would be these coatings, these topographical modification approaches would reduce the potential of loss of invested value in that wind turbine and in that wind farm. So just to kind of summarize, there's 10 technologies that I showed on that second slide or third slide earlier. We have developed many of these to be scalable, right? That's really important, to be relatively affordable for the application space. The durability in the operational environment, I touched on that briefly, but we've done a lot for these technologies to demonstrate their durability. And then finally, environmental awareness. You know, the whole point of having a wind turbine is to keep the environment clean. If our coating is shedding these harmful organic materials, that's very much so counterproductive. And then finally, there's my contact information. And I guess at this point, I'll turn this over to Grady.
Okay, thanks, Chris. Sorry, I'm having some broadcast difficulties here. And okay, well, thanks for joining us this afternoon. My name is Grady Koch. I'm a researcher at NASA Langley. I specialize in making wind measurements and building technology called LiDAR for making wind and atmospheric measurements. So I wanted to discuss for you today a concept we call the wind event warning system. And this is a LiDAR, which is a lot like a radar, except it uses pulses of light from a laser to give a predictive capability for oncoming hazardous wind events. And so we could conceivably create a prediction of 10 to 30 minutes of the possibility of a severe wind event, like a wind shear, severe gust, storm outflow, that could possibly damage a wind turbine. And so with that amount of warning, hopefully the turbine could take protective action, such as feathering the blades so it didn't incur a severe wind loading on it. In addition to that sort of catastrophic incident protection, which is hopefully a rare event, this technology could also give predictions of the far more gentler occurrences that are fairly common, in which you have a oncoming change in the wind, say from a different cold front or a warm front coming in, and there would be a boundary in which the wind vector would change, and this would in turn change the output from a wind farm. So in turn, a operator of an electrical grid could know whether to spin up or spin down another power generation capability to keep the load balanced. So cost benefit of this technology is in two potential areas. One is avoiding the catastrophic damage to turbines, and also to help optimize the supply to the electrical grid. So this concept came from a long history of measuring wind with LiDAR at NASA, and NASA was approached by several people concerned about putting wind turbines offshore, and in particular offshore of Virginia Beach. And we were asked if there was a way to measure winds way out in the ocean while staying on shore from a convenient location. So the answer to that question is yes, you can. So we did a demonstration measurement with the LiDAR. And so in the upper right here, I have just kind of a quick tutorial on how this technology works. You pass a laser beam into the atmosphere and it reflects off of atmospheric aerosols. So aerosol is a fancy word for dust. This dust is naturally in the atmosphere, and it will reflect a little bit of the laser light. And since that dust is in motion with the ambient wind field, by measuring the Doppler shift from the dust, we can measure what the wind field is. So you get a wind measurement that is resolved with distance, and you can make wind measurements from a remote location. So, for example, we positioned one of our LiDARs at Fort Story in Virginia Beach and pointed it out into the Atlantic Ocean and Chesapeake Bay. And so some quick example measurements of this to measure the wind flow offshore. In the upper right, we have an example measurement in which we look at the speed of the wind as you travel perpendicular to the ocean front. And this is a good explanation of why offshore wind power will work pretty well. As you can see near the shore, you have a wind speed of about 5 meters per second. And that increases, though, when you go about 5 kilometers or more to about 12 meters per second. So with wind energy being related to the cube of wind speed, this factor of more than doubling the wind speed would give you something like around a factor of 10 higher output from your wind farm. So this is well known that you want to position your wind farm and your turbines in locations where you have the highest possible wind. We have another example of measuring wind in the vertical direction. So these are wind profiles. So in these two plots, we have wind speed as the top colorful graph and wind direction as the lower colorful graph, and the vertical axis is altitude in meters. So these measurements are going up pretty high, about a kilometer high, and we can see the wind variation with altitude, which is usually quite interesting and wonderfully complex. Of course, turbines are going to be at much lower altitudes, but just to show the capability where we can measure changes in wind fronts that are even pretty gentle. So in this example, you see in a lower plot where I've drawn a line and a label of frontal wedging. So this is where you have a different air mass moving into the area. And you can see with plenty of warning time that you're going to be having a change in the wind vector as time develops. So we did these measurements really for customers who wanted to know simply what the wind speed is, but it became apparent to us that we could also, with certain strategic scanning patterns, create a warning of when the wind might be changing, and hence the patent on this technology. Now, this patent went in and came out in 2018, so it's a few years old. We had some initial licensing discussions and got feedback that this is a wonderful idea, wonderful data. However, the instrument is just too expensive if we copied the approach that we had taken. So this instrument is about $2.5 million to duplicate. So taking that feedback, not just from this application, but many potential customers would like to see this technology come down in price so we could find more use in many different applications. We began looking into, well, how do we reduce the cost? And the key factor is in the laser transmitter, which in the original NASA design is a very sophisticated, very complex, one-of-a-kind instrument based on a solid-state laser material of holmium in a host of yttrium lithium fluoride. It's a very unique laser material. There has been, however, a recent breakthrough in the past few years in lasers that are built into optical fibers. And we have these lasers coming in to a similar design combined with a receiver and the signal processing and the electronics that form the basis of this patent. That is really, this patent is more toward the signal processing, the way you look at the data. It could work with a variety of different laser or optical designs. But using this new laser technology, we feel we can get the price way down, factor of 4 or 5 less than our original estimates. And we would be able to reach out to distances of about 10 kilometers. So this is sort of the concept simply drawn of what we envision, that you would have a LiDAR located at your wind farm location, which is represented by the blue dot in the middle of the circle. And that wind farm is operating in a large scale flow field represented by the green arrows to show the wind vectors. But you have these occasional events where you have, say, a gust front drawn by the purple line in the upper left there, and behind that gust front you have a change in the wind vector. So in this case, the wind vector would be a change in direction and an increase in speed compared to what the wind farm is currently experiencing. So with the distance capability of the system, you would have something easily 10 minutes of warning time to know that gust front was coming in and to make changes. So I should point out that this LiDAR technology does exist commercially. However, it uses lasers that are pretty low power, and they can only reach out to about 1 kilometer, which is probably not enough warning time. So the innovation that NASA is working on is increasing the distance capability. So with the new fiber lasers we have coming in that are much more reasonable cost, we feel reaching to 10 kilometers distance and giving that tens of minutes of warning time is quite feasible. So with that, let me conclude.
This NASA technology and many others are ready to be transferred to your business. Find out more by visiting technology.nasa.gov.